Hello and welcome to Chapter 9 of our course, Cratered Worlds. After this chapter, you will understand the lunar explorations, the composition of our moon, different surface features and properties of lunar soil, the history of the lunar surface, lunar craters and their formation, as well as Mercury's orbit and structure and composition. Our first section of this chapter will cover the general properties of the moon. The moon has an eighth of the mass of the Earth and only a sixth of the surface gravity. Because the gravity is too low, there is no formation of an atmosphere. Sometimes there is what is called a temporary atmosphere from impacts, but the gas either escapes or freezes to the surface of the moon. So there is no permanent atmosphere on the moon. In terms of lunar exploration, we've had 9 Apollo trips to the moon. Initially, we orbited only, and then we began landing on flat areas. As NASA gained confidence, more and more geologically interesting areas were explored and more time was spent there. As the trips became less about achievement and more about scientific inquiry, eventually a geologist would join the crew. We gained more and more knowledge from each visit we took to the moon. Here we can see the famous photo of astronaut Edwin Buzz Aldrin on the surface of the moon erecting the U.S. flag. Here we can see the two sides of the moon. Before our space explorations to the moon, we only studied about 1 kilometer on the side of the moon facing the Earth. And here we can see a photo of the geologist that was among the crew on the last Apollo mission. The Apollo missions accomplished 3 important objectives. First, nearly 400 kilograms of samples were collected. Second, 8 Apollo lunar surface experiment packages were deployed which were able to operate for years after the astronauts left. And third, the orbiting modules were able to photograph and analyze the surface of the moon from above. Here we can see some of the samples from the moon being analyzed back on Earth. These samples taken from the moon provided more information about the moon than every other lunar exploration before it combined. They are essential to our understanding of the moon. Here we can see one of the rockets that was planned to go to the moon. The moon exploration stopped before it was deployed due to economic and political pressures. The US and Russia have no current plans to take us to the moon again, although China does seem likely to try. From these explorations, we know that the moon is made almost entirely of silicate rock, depleted in iron and other materials. It is as if the moon is composed of the same silicates of our mantle and crust, but with the metals removed. The seismometers taken to the moon confirm that the moon has no large metal core. Initially, we attributed some of the water detected as coming with us from Earth's atmosphere. However, scientists have concluded that some chemically bound water is present in the lunar rocks. Water ice has been detected in permanently shadowed craters near the lunar poles. We estimate the total water in the polar craters to be hundreds of billions of tons. As a liquid, this would only be enough water to fill a lake 100 miles across. However, compared with the rest of the dry lunar crust, this is a lot of water. We infer that this polar water was carried to the moon by asteroids that have impacted the moon. One reason this discovery could be important is that it raises the possibility of future human habitation near the lunar poles, or even of a lunar base en routes to Mars and the rest of the solar system. If the ice could be mined, it would yield both water and oxygen for human support, and it could be broken down into hydrogen and oxygen, which is a potent rocket fuel. Now that we've discussed the general properties, we're going to talk in more detail about the lunar surface. Here we can see the central mountain peaks of Tycho crater on the moon. It is 82 kilometers in diameter and one of the most recent craters on the moon. The main peak is 12 kilometers above the crater floor. For reference, Mount Everest is 8.8 kilometers in height. If you look at the moon with a telescope, you can see that it is covered by impact craters. With the unaided eye, you can see vast splotches of darkness. In the past, lunar observers thought the moon had continents and oceans that could contain life. They saw the dark shadows as seas and the brighter areas as continents or land masses. They named the seas, like the Sea of Clouds and the Sea of Tranquility. We still use these names today. The areas of land were not named. However, they named individual craters after great scientists and philosophers. Some of the most prominent craters are named after Plato, Copernicus, Tycho, and Kepler. Galileo is named after a small crater, which reflects his low standing among the Vatican lunar cartographers. When we studied our samples from the moon, we used radioactive dating on the lunar rocks brought back to Earth. The dates ranged from 3.3 to 3.4 billion years old, older than most rocks on Earth. Remember that the Earth and the moon were formed 4.5 and 4.6 billion years ago. Earth's geological activity makes it less likely that rocks that old are preserved. The lunar highlands are areas of low-density rock which solidified on top of the heavier rock during the formation of the moon. Since they formed so early in lunar history, they bear craters from billions of years ago. They make up about 83% of the lunar surface. Here we can see the lunar highlands with their heavily cratered surface. Notice that their high points are not points. This is because Earth has peaks from erosion due to atmospheric activity. The moon does not experience erosion, so the peaks remain round. Here we can see a photo from the Apollo missions of another smooth mountain on the moon's surface. Here we can see the remaining 17% of the moon's surface, which is the lunar Maria. This Maria consists of volcanic lava which erupted billions of years ago. These lava flows filled in the impact areas from the moon's early history, so we see less craters on it. This volcanic lava, or basalt, is similar to the crust under the ocean and lava from volcanoes on Earth. Since the early history was erased by eruptions, we do not know exactly when they began, but we do know that they ceased about 3.3 billion years ago. Here we can see a rock from the Mar. When lava forms rocks, they are left with bubbles, which you can see here. Lunar rocks are chemically different from terrestrial rocks. This has allowed scientists to identify lunar samples among the thousands of meteorites that reach Earth. Here we can see the youngest basin in the lunar Maria. Basins are the names we give to the craters filled in by volcanic lava on the moon's surface. This basin is 1,000 kilometers wide and not completely filled with lava. Next, we'll discuss what it actually feels like to be on the moon's surface. Immediately upon stepping onto the surface, Neil Armstrong said, "The surface is fine and powdery. I can pick it up loosely with my toe, but I can see the footprints of my boots and the treads in the fine sandy particles." The surface of the moon is buried under fine-grained soil that Armstrong was talking about. This soil is made of shattered rock fragments. Like much else, this is due to years and years of impacts on the moon breaking up the rock and then spreading it around. Here we can see a footprint in this lunar soil from one of the Apollo missions. Without an atmosphere, the lunar surface experiences greater temperature extremes than Earth, despite being the same distance from the sun. During a lunar day, which lasts 2 Earth weeks, temperatures reach the boiling point of water. Lunar rock is porous, so it cools much quicker than Earth's dense rocks. Combined with that and the lack of atmosphere, the lunar night is accompanied with a drop in temperature to negative 173 degrees Celsius, which is about negative 280 degrees Fahrenheit. Our next section will discuss the Moon's impact craters. Unlike the Moon, the Earth has been battered by outside forces. However, because of geological activity, most of the Earth's craters have been erased from the surface. The Moon, however, still has many evidences of impacts. Before the 1890s, scientists assumed that the lunar craters were volcanic craters. Grove K. Gilberty noted that the terrestrial volcanic craters are smaller and deeper and almost always occur at the top of volcanic mountains. Therefore, the only other reasonable explanation is an impact causing lunar craters. Here we can see the difference between volcanic and impact craters. Volcanic craters are deeper and smaller than impact craters. However, Gilbert was still unsure of why these craters were not ovals, and the answer to this lies in the object's velocity. To escape a planet, an object has to overcome what we call an escape velocity. This is the minimum velocity an object has to travel with in order to escape an object's gravitational force. When being pulled to a planet or moon, the minimum speed the object will have is this escape velocity. This is because this velocity is the velocity the object would have to overcome the force of gravity as it travels away from the planet. Since it's the same force pulling the object in, it will eventually accelerate to this velocity upon reaching the surface. Since the objects have an initial speed, objects crashing into a planet will hit the planet with this initial speed plus the escape velocity of the planet. When striking the planet, the energy this object has from its velocity is expelled. The time of the collision is very short. Therefore, a large amount of energy is expelled in a very short amount of time. This is an explosion. The explosion excavates a large volume of material around the impact site in a symmetrical way. This is why impact craters are circles. Unfortunately, like many scientists, Gilbert did not live long enough to see his hypothesis become widely accepted. Let's talk about how exactly the impact crater is formed. When a fast projectile impacts the surface, it penetrates 2 to 3 times its own diameter. The kinetic energy from the projectile is then transferred into heat and a shock wave which spreads out symmetrically from the object. This shock wave penetrates the planet and the heat vaporizes silicate, which expands into an explosion. The explosion is like detonating a nuclear bomb on the surface. The combined shock wave and explosion excavates a volume of material symmetrically around the impact. This is the crater. In general, the size of the crater becomes 10 to 15 times the projectile diameter. Here we can see a play-by-play of the impact. The projectile approaches at escape velocity plus its initial velocity. The projectile penetrates 2 to 3 times its diameter into the surface. The shock waves penetrate and fracture rock further into the surface, while the escaping heat causes an explosion. Then a circular impact crater is formed. Here we can see one of these impact craters. The word crater actually comes from the Greek word for bowl. When a crater is formed, larger pieces can actually break off and form smaller craters up to kilometers away. Here we can see our moon. When our moon is fully lit, sunlight is hitting it directly. This exposes more contrast between its light and dark surfaces. However, not much of the topography is exposed here. When the sunlight is coming in at an angle, like during a waning or waxing crescent or gibbous, or the first or third quarter, the sunlight casts stark shadows of the lunar surface's topographical features. This makes them easier to see and study. Since the moon has little erosion and internal activity, we can use crater counts to estimate the time since the surface had a major disturbance. We cannot directly measure the rate between large crater-forming impacts, since the time between them occurring is longer than human history. However, we can estimate it by the number of potential projectiles in our solar system. We can also estimate it by the amount of craters on the lunar Maria. Both lead to similar estimates. These numbers matching with carbon dating indicates that astronomers are correct to assume that impacts occur at a constant rate. However, we have reason to believe impacts were much more frequent when planets were forming. This is because the highlands are not wiped by geological activity like the Maria. They show way more craters than the Maria, though. If the impacts were at a constant rate when the highlands were first formed, it would indicate they were formed 38 billion years ago. The only explanation is that the impacts were much more frequent when our solar system was first being born. In summary, since the planet's forming, we've had constant rates of impact. Since the Maria has hardened, impacts have been at a constant and predictable rate. When the planets were first formed, impacts had to be more common and frequent. This is evidenced by the highlands, which are untouched by geological activity since the formation of our solar system. Here we can see the approximate variations in impact frequency over the course of billions of years. Since the Maria was formed, we can see that the impacts have been at a constant rate. Before the Maria formed, impacts had to be much higher. We only have a hypothetical maximum for impact rate. Our next section will discuss the origin of the moon. There are three main theories for how the moon formed. The first is the fission theory, which theorizes the moon was once part of Earth, but somehow separated from it early in their history. Second is the sister theory, which theorizes that the moon formed together with, but independent of, Earth, as we believe many moons of the outer planets formed. The third theory is the capture theory, which theorizes that the moon formed elsewhere in the solar system and was then captured by Earth's gravity. However, there are problems with both the fission and the capture theory. The contradiction with the fission theory is that modern calculations have shown the sort of fission or splitting theorized is not possible. The contradiction with the capture theory is that, to go into orbit, the object traveling would have to lose a significant amount of energy. No one has come up with a way that the Earth would have been able to capture something as big as the moon. Additionally, a capture like this would likely force the moon into a shaky orbit, not a circular orbit like we see. Also, that does not explain how the moon has the exact percentage of oxygen isotopes as Earth and is made of the same materials without the heavy metals. The sister theory has since become The sister theory has become the most generally accepted theory. The sister theory that the moon was formed alongside Earth leads up to the giant impact hypothesis. The giant impact hypothesis envisions Earth as being struck by an object approximately 1/10 of Earth's mass, about the size of Mars. This is close to the maximum impact Earth could take without being shattered. This impact would eject a vast amount of material into space, releasing almost enough energy to break the planet apart. This ejected rock vapor then cooled and formed a ring of material orbiting the Earth. This ring then condensed into the moon. When this impact happened, heavy metals had already sunk into the Earth. This explains why the moon is only made of the materials we see in our mantle and any materials from the projectile itself. This is the most generally accepted hypothesis of the creation of the moon. Now that we've discussed the moon in more detail, our next section will talk about Mercury. Mercury is the closest planet to the Sun. Just as Kepler's law says, Mercury then has the shortest period of revolution at 88 days. It has the highest orbit speed at 48 kilometers a second. Mercury has an eccentric orbit which takes it anywhere from 46 million kilometers from the Sun to 70 million kilometers from the Sun. Mercury is also the smallest terrestrial planet at 1/8% of the Earth's mass. Mercury's composition makes it unique amongst the planets. It is much denser than the Moon, indicating that it has a much different makeup than our Moon. It has an iron-nickel core which makes up 60% of its mass. Mercury can be thought of as a metal ball the size of the Moon, surrounded by a rocky crust 700 kilometers thick. We observe a magnetic field from Mercury, implying that some of the metal core is liquid. The metal field is consistent with a very large core. Here we can see Mercury's internal structure. As you can see, it has a very large metal core the size of our Moon. Radar observations have shown that Mercury does not keep one side fixed towards the Sun. To make a radar observation of a planet's rotation, we send out a transmitted signal. There is something called a Doppler shift in the return signal, depending on if the planet is rotating or not and how fast it's rotating. We have seen that it takes 59 days to complete a rotation. This is the first case demonstrating that a 2:3 ratio of spin to orbit of a planet is actually stable. Here we can see the radar observations used to determine Mercury's rotation. We had to use this rather than just observing Mercury, since Mercury looks the same from any side visually. Mercury experiences the biggest change in temperature of any planet. During its day, the surface temperature becomes 430 degrees Celsius, or a whopping 806 degrees Fahrenheit. Since there is no atmosphere, the surface cools very quickly during dawn, and the side currently facing away from the Sun cools to a negative 170 degrees Celsius, or negative 275 degrees Fahrenheit. Mercury's surface was first looked at closely in 1974 by spacecraft Mariner. In 2011, Messenger spacecraft mapped Mercury in great detail. Mercury's surface resembles the Moon. This is why it is in this section of the lecture. It is cratered and also has past volcanic activity. Messenger verified water ice seen by the radar at the poles. Messenger also made the unexpected discovery of organic or carbon-based material in this water ice. Here we can see Mercury's topography. The lowest regions are shown in purple and blue, and the highest regions are shown in red. The difference in elevation between the lowest and highest regions shown here is roughly 10 kilometers. As you can see, Mercury's surface very closely resembles the surface of our Moon. Here we can see the Caloris Basin. This partially flooded impact basin is the largest known structural feature on Mercury. The smooth plains in the interior of the basin have an area of almost 2 million square kilometers. Most of the Mercurian features have been named in honor of artists, writers, composers, and other contributors to the arts and humanities. This is in contrast with the scientists commemorated on the Moon. Among the named craters are Bach, Shakespeare, Tolstoy, Van Gogh, and Scott Joplin. There is no evidence of plate tectonics on Mercury. However, the planet's distinctive long scarps can sometimes be seen cutting across craters. This means the scarps must have formed later than the craters. These long, curved cliffs appear to have their origin in the slight compression of Mercury's crust. At some point in its history, the planet shrank, which wrinkled the crust. This must have been done after most of the craters on the surface had already formed. If the standard cratering method applies to Mercury, this shrinkage must have taken place during the last 4 billion years and not during the solar system's early period. Unlike the Moon, Mercury is dominated by its metal core. Astronomers think Mercury should have a similar composition to the Earth and Moon, and the most likely explanation is that it lost its rocky material in a collision or multiple collisions which tore away its crust. That's the end of Chapter 9. Make sure to watch the Chapter 10 lecture next.